Okay, last little mini half lecture. Let me start the timer. Um, Last one. I have to admit, despite really enjoying the material in this class and really enjoying teaching y'all, it's been a challenge over the past couple weeks. But that's life, and it's gonna be my summer too, and maybe my fall, so better get used to it. Right, so what we're going to do here for the last day is just continue playing around with some further combinatorial identities. So further combinatorics with binomial coefficients. Okay, so we were playing a lot with binomial coefficients last time, and we're going to kind of do more. Okay, so to start with, let's talk about van der Moen's identity. Okay, so this is the following. This is a theorem that m plus n, choose r, is going to be equal to the sum over k is equal to 0 up to r of m and r minus k, m choose r minus k, and then n choose k for r less than or equal to n and r less than or equal to m. So probably I should have said for a triple of integers, m, n, all greater than or equal to 0, with r less than or equal to n and r less than or equal to m, then we have the following relationship, that m plus n choose r is equal to the sum from k is equal to 0 up to r of m choose r minus k times n choose k. And here we're going to do, once again, a combinatorial proof. We can describe this number as the cardinality of some set, right? So the proof, the left-hand side, m plus n, choose r, is the number of subsets of cardinality r in a set of cardinality m plus n. Okay, so this thing is just saying, if you start with a set of size m plus n, how many ways can you find size r subsets of that set? And there are precisely this number. That can be taken almost as a definition of this symbol. On the other hand, let's try to think about what this is counting. The thing that's most striking here is that this is the number of subsets of size k in a set of size n, and this is the number of subsets of size r minus k in a subset of size m. So essentially what we're thinking about is, here we're picking r subsets of a union, and here we're viewing two different sets, right? So let A and B be sets such that the cardinality of A is equal to m and the cardinality of B is equal to n. So we're going to interpret this left-hand side as being R subsets of A union B. We're going to assume that A and B are disjoint. Okay, so let A and B be set such that the cardinality of A is m, the cardinality of B is n. Then if we forget this summation, what we're doing is we're picking k elements from set n, and we're picking r minus k elements of set m. Well, every subset of A union B you can kind of think of as, what elements from A does this subset contain, and what elements from B does this subset contain, right? So in particular, another way to count R subsets is choose k elements in B, or a k element subset in B, and an r minus k element subset in A. There are m choose r minus k times n choose k ways of doing this for each k. And then you just sum over all the possibilities of how many you take from n. You can either take 0 all the way up to r, which is take every single element of your set from set n. This is summing over all the possible ways of getting R element subsets, but just counting it differently. You're just counting any given R element subset. You're saying, what is the intersection of this R subset with B, and what is the intersection of this R subset with A? So since each of these sides is counting the same thing, these two sides must be equal. So both sides are counting R element subsets of A union B. And this, of course, leads to a whole bunch of other corollaries, one of which would just be the following. For n greater than or equal to 0, 2n choose n is equal to the sum from k is equal to 0 up to n of n choose k squared. It's a weird looking identity. It looks bizarre. It doesn't look like the ones that we've been dealing with before. But the proof is just use Vandermonde's identity with m is equal to n is equal to r. So then we'd get 2n choose n is equal to the sum from k is equal to 0 up to n of n choose n minus k times n choose k. But what do we know about n choose n minus k? Well, that's the same as n choose k. So this is the sum from k is equal to 0 up to n choose k, and n choose k. Right? The number of ways of choosing subsets of size n minus k is the same as the number of ways of choosing subsets of size k because they're complementary. Right? If I have a set of size 100, picking 5 elements, selecting a 5-element subset also defines a 95-element subset, which is everything that got left behind. Great. So this is Vandermonde's identity and two things, and a corollary that comes out of it. The next one that we're going to do is going to be the hockey stick identity. I'm sure it has another name, but hockey stick identity is a fun one. Yeah. So next example is the hockey stick identity. Maybe I ought to do an example of what the hockey stick identity is first before we write down a formula and start proving. Let me write Pascal's triangle. So Pascal's triangle looks like this. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, etc., etc. So the important point to note is the following sort of idea. If I pick any element inside the triangle, like let's say I start with 20. The thing that I know about 20 is that it is equal to the two things above it, right? This is Pascal's identity. 20 is equal to the sum of these two elements, right? So what I'm going to do is I'm going to say, okay, it's 10 plus 10, but this 10 right here is equal to the sum of these two elements, right? 10 is equal to 4 plus 6. And so I've got 20 is equal to 10 plus 10, but this 10 is going to be written as 4 plus 6. And this 4 I can actually rewrite as 1 plus 3. I'm kind of going all the way up, right? So in other words, this 20 is also equal to 10 plus 6 plus 3 plus 1. And since this one is the same as this one, I actually get what looks like a hockey stick, which says this number, I've never played hockey. I have no idea what the bottom of a hockey stick is. This bit where you hit the puck with is actually equal to the sum of the diagonal that lies above it, like this. And indeed, 20 is equal to 10, 16, 19, 20, right? We could do the same thing over here. 15 is equal to 5 plus 4 plus 3 plus 2 plus 1, right? This is 9, 12, 14, 15. The idea is that every time you kind of repeat Pascal's identity. You start off with a number here. This is going to be equal to this sum. You hold on to this number, and then you expand this 10. And then you hold on to this number, and then you expand this 4. And you hold on to this 3, and then there's 4 is equal to 3 plus 1, but the 1 right here is just the same as the 1 right here. So essentially we're kind of repeatedly using Pascal's identity to kind of break down the numbers along this diagonal. So, and there are plenty of identities that kind of follow this kind of tracing pattern throughout Pascal's triangle. Written in notation, this looks as follows. This looks as the sum from k is equal to 0 up to r of n plus k, choose k, is equal to n plus r plus 1, choose r. So this n plus r plus 1, choose r, is going to be our term somewhere inside the Pascal's triangle. And then this sum, as k increases, this is kind of moving along a diagonal, right? Let's say that we start with n is equal to 2. So this is 0, choose 0. This is 1, choose 0. This is 2, choose 0. So 2, choose 0 is 1. Maybe I should write it down over here. 0, 0. Here's another version of the Pascal's triangle. 1, 0, 1, 1. Here's 2, 0, 2, 1, 2, 2. Here's 3, 0, 3, 1, 3, 2, 3, 3. And then here's 4, 0, 4, 1, 4, 2, 4, 3, 4, 4, and so on and so forth. So this sum from k is equal to 0 up to r of n plus k, choose k, that kind of looks like one of the diagonals, right? If n is 1 and k starts at 0, then it's 1, choose 0, plus 2, choose 1, plus 3, choose 2, plus 4, choose 3. Or maybe if you start somewhere else, if you start at 3, choose 0, then it's 3, choose 0, n is 3, plus 4, choose 1, plus 5, choose 2, plus 6, choose 3, and so on and so forth. So you can really see that what this is telling you to do is to sum across a diagonal. Of course, if I flip this and made this n plus k choose n, right? N plus k choose n has to be the same as n plus k choose k by the complement rule. Now this looks like summing across one of these diagonals, right? I could start with k is equal to 3 and k is equal to 2, n is equal to 0. Then I'd be at k choose, k choose 0. 2 choose 0, 3 choose 1. Oh, no. That's counting the same thing. There should be a nice way to kind of reverse the direction of the hockey stick, so to speak. But I can think about that later. Anyways, replacing this with this will certainly give you the correct answer. Yes. What am I after next? Okay, right. So this is kind of giving us some motivation for why this hockey stick lemma looks like this. And then the proof is, in this case, just going to be induction. Proof by induction. Well, first let's figure out what the base case is. We're going to induct on K. First, the base case, when K is equal to 0, well, then this identity is just saying the sum from K is equal to 0 up to 0 of n plus 0 choose 0 is equal to n. Wait a second. Am I doing this right? Yes, I am doing this right. N plus 0 plus 1 choose 0. Well, the sum from 0 to 0, that's just one term. N plus 0 choose 0. What's n choose 0? N choose 0 is just 1. And what is n plus 1 choose 0? It's also 1. So this identity holds when K is equal to 0. Now for the inductive hypothesis. I'm just going to say that the sum from K is equal to 0 up to L holds. So that is the sum from K is equal to 0 up to L, n plus K, choose K, is equal to n plus R plus 1, choose R, L. Sorry, I'm inducting on R here. I'm not inducting on K. I'm so sorry. Induct on R. Oh, that's going to be kind of disastrous. Right, I'm inducting on R. Base case R is equal to 0. I'm going from 0, K is equal to 0, up to R is equal to 0. And now I have n plus K, choose K, but in this case it's just going to be n plus 0, choose 0. And I get the same thing over here. Now this holds. Okay. Whew. Inductive hypothesis, this holds up to L. And what we want to show is we want to show it holds for n plus L plus 1, or L plus 1. Show it holds for L plus 1. R is equal to L plus 1. Holds for R is equal to L. Need to be careful about the indexing here. Sorry about the confusion. So the inductive hypothesis, it holds up to R is equal to L. I want to show that it holds for R is equal to L plus 1. So what I do is I'm going to start off by writing this side. On this side, n plus L plus 1 plus 1, choose L plus 1, right? This is this term where R is equal to L plus 1. This is going to be equal to, by Pascal's identity, well, what is it going to be equal to by Pascal's identity? You remember that you shrink the top layer, right? If I start with 3, 1, that's going to be 2, 0 plus 2, 1. So this is going to be equal by Pascal's identity to n plus L plus 1 plus n plus L plus 1. And then here is going to be L plus 1, and here is just going to be L. Hey now. Sorry, little guy. Okay, and now we should be using our inductive hypothesis. By the inductive hypothesis, this term right here is equal to a big sum. So this whole thing is equal to a sum from k is equal to 0 up to L of n plus k, choose k, plus n plus L plus 1, choose L plus 1. But this fits right into the sequence. So this whole thing, this is just the next term where I'm adding up to L plus 1. So this whole thing is equal to the sum from k is equal to 0 all the way up to L plus 1 of n plus k, choose k. Okay. I would say it's a good practice of your inductive skills to go through this and make sure you understand the proof. And I've made it challenging by messing up, not messing up, but being unclear about what what number I was inducting on. So that's an extra fun challenge for you. Ha ha. And an alternative thing to let you know is that there's also a combinatorial proof where you interpret this essentially as subsets of size r of a set n plus r plus 1. The way that you think about these subsets is, once again, you think about bit strings, that is strings of zeros and ones. And so essentially you're saying, if I want to choose a subset of size r, that's the same as picking from a bit string. You choose r places to put zeros, and you choose n plus 1 positions to put ones. And then you view this sum as saying, what is the position of the last one? Like, if all the ones are on one side, then there are n plus 1 ones, and then a whole bunch of zeros, and there are no choices. But if the last one is at position n plus 2, let's say, I'll just try to sketch out what I'm saying here. Just the idea. Like, let's say that this is slot 4, and there are 3 ones. Then this is the last one, so 2 of the ones are going to go somewhere in here. And so out of 3, I'm going to choose 1, 0. So I'm going to have a 3 choose 1 appearing here. Or what if the last one is in slot 5? Well, there are going to be 4 slots. I'm going to choose 2 of them to be 1s and 2 of them to be 0s. So that I'm going to have n plus 2 choose 2. And similarly, what if the last one is in the 6th slot? Well, then I'm going to have 5 slots. I'm going to have n plus 3 choose 3 because I'm choosing 3 slots to put zeros and filling in the rest with ones. Anyways, I don't want to spend a lot of time on it, but there's also a combinatorial way of thinking about these two things counting sets in the same way. Or counting the same set in different ways, more particularly. I don't know if you can hear my roommate. Hopefully not. Okay, let's do one last little exercise, or one last interesting thing, one last counting task. Last counting task. And this one, if you go on to do more math, you might find surprisingly useful. So what it is count the number of monomials of degree k in monomials of degree k in n variables. Okay, so this is essentially working with polynomials in several variables. So let me give you an example. I'm going to look for degree 3 monomials in 3 variables. So I'm going to pick my variables to be x, y, and z. So my monomials are going to look like x cubed, y cubed, z cubed. These are all the ones, these are monomials of degree 3 where it's only one of the variables. Then let's look at all the monomials of degree 3 that have two variables involved. There's going to be x squared y, x squared z. We're going to have x squared y, x squared z, y squared x, y squared z, and finally z squared x, z squared y. These are all the combinations where I only have two. And then last I'm going to have x, y, z. Right? So these are degree 3 polynomials, but they're maybe not polynomials that you're used to seeing because they're in three variables, x, y, and z. Well, actually, you've taken Calc 3, so you should be very familiar with these. I take that back. Okay, so the number of degree 3 monomials in three variables is 10. 1, 2, 3. And this is up to scalar. I'm not counting multiplying by a scalar. I'm just counting these. Okay. Let me introduce you to an idea of how we count these. The idea is I want to think of baskets. So I'm going to have some basket which is associated to x's. I'm going to have another basket which is associated to y's, and I'm going to have a third basket associated to z's. And I'm going to come up with a counting scheme that allows me to denote one of these monomials. So there are three baskets. So what I'm going to do is I'm going to really think of that as being divided by two ones. And so now all this space is where the x's live, this space is where the y's live, and then this space is where the z's live. So the ones, the two ones, correspond to partitioning the real line into three chunks, basically. And now I'm going to think about putting zeros somewhere in here, and it's going to denote how many x's I take, how many y's I take, and how many z's I take. So for instance, 0, 0, 0, this corresponds to x squared z. And something that looks like xyz would look like this, xyz. And similarly, z cubed would look like this. All right? So now you can kind of see what I've done. I've brought it back into the choose notation because, as we've said a couple times, choosing a subset of a certain cardinality is essentially, if you're choosing it from a finite set, it's ordering the elements and then putting a 0 between each element that you want to leave and putting a 1 between each element you want to keep. So strings of zeros and ones should remind of a fixed length should remind us of choosing. Right? In particular, what we're going to see is that if we have 5 slots and we're going to choose 2 ones and the rest are going to be zeros, that's the same thing as 5 choose 3, or of course that's the same thing as 5 choose 2. Either of these are equal to 5 factorial over 2 factorial times 3 factorial. And we get exactly 5 times 4 over 2, which is equal to 10. So indeed, 5 choose 3 or 5 choose 2 is counting the number of degree 3 monomials in 3 variables. And from here, you can already see how to generalize. How to generalize. The idea is if you have n variables, you should have one less number of ones, and you can think of them as the dividers, right? The dividing lines between your baskets of your n variables. So for instance, say I had 4 variables, x, y, z, w, then I would need 3 ones, so that in here were the x's, in here were the y's, in here were the z's, and in here were the w's, right? So what I need a set of size n minus 1. This corresponds to how many 1s you need. And then how many zeros is the degree of the monomial, right? If I want a degree 5 monomial in x, y, z, and w, I need 5 zeros, like 2 here and 3 here. This corresponds to x squared z cubed, right? A degree 5 monomial in 4 variables, I need 5 zeros to put inside the 4 baskets. The 4 baskets are delineated by 3 dividers. So it's n minus 1 plus k. I need as many zeros as the degree, so that this whole sum is equal to n plus k minus 1. For instance, 3 monomials and 3 variables, and the numerator in the choose should be 5. Right? I'm choosing from a 5-element subset. And then I either choose k, right? I can either choose the k places to be, or I can choose n minus 1 plus k, choose k. Oh, I'm sorry, choose n minus 1. We know that these are equal. So these are the one thing that they count are monomials in n variables of degree k. And this idea of partitioning things like this is called the stars and straps, or stars and bars, because it's, I suppose, nicer to draw stars than to draw zeros. But the idea is you're looking at, you know, once again, you're looking at bit strings, right? If this represents some monomial in 1, 2, 3, 4, 5 variables of degree 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? This is, let's say that this is x, y, z, w, q, then this corresponds to x squared, y squared, z, w cubed, q cubed. And this is how you count them. Okay, so I'm not giving you any homework on this binomial theorem stuff, but I hope you enjoy it. I hope that you think about it. This binomial counting stuff is very deep and very rich, and you can go a long, long way with it mathematically. Overall, I've really enjoyed teaching this class, despite the difficulties. I hope you've enjoyed it as well. Please fill out the evaluations, and please leave me comments about my teaching online. Please give me some feedback so I can try to improve my teaching. Your feedback and comments are really helpful to me. So I'd really like to hear from you on the feedback, and I mean, hopefully at the end of the semester you're doing all right, and you and your family and friends are doing all right. So yeah, best of luck on the oncoming finals that you've got. Oh yeah, I should probably say some things. So our final will be Friday, May 1st. I'm going to do the same thing that I did with the midterm 3. I'm going to write a test. I'm going to not write a 3-hour exam, but you'll have 3 hours within which to take the exam. But I'm going to give you a 24-hour time slot. And so anytime starting Friday at 12, oh shoot, I should check what time slot it is. But basically starting at our traditional final hour, Friday, May 1st, you'll have 24 hours. And in that 24 hours, you should take the exam for 3 hours. I think that the video thing was not so helpful after all, so I'm going to try to write creative problems that are not easy to look up or cheat on. So yeah, I'm just going to be giving you 3 hours to do a test starting Friday, May 1st. Email me if you have any questions. I will work to make your grades available on the midterm tomorrow. All right, great. We're done.